Welcome back to Organic Chemistry. Let's have a look at the different ways that we can draw molecules so that we can think about them a little bit further. So if we have the molecule that we were looking at just last time, which would be this one here, we can draw this in a variety of ways. My favorite, or the most closest to reality, would be the wedge dash convention, where a wedge would define a bond coming towards you, and a dashed wedge effectively defines a bond going away from you. So we define the plane, and the best way to do this is to put two bonds in plane so that they become lines, and then we have slightly, so that we can draw it, we slightly manipulate the molecule, so we tilt it slightly like that. So we've got the one in plane, which would be the OH, and we've got the one that's also in plane, which is the nitrogen, and then we've got one coming towards us, which is this hydrogen. Woo, it looks weird to you. So this hydrogen here, put my finger there, so it looks weird because the camera is not working, you're not getting the perspective properly. So we've got this one coming towards us and this one going away from us. So if we draw that, we would have OH, and we would have, what was the bottom one? That's an N, and that was obviously going to have some hydrogens on it. And then we have a wedge to show the hydrogen coming towards us. And we have a dotted wedge, which starts off big and gets small for the chlorine. So that is a way of drawing molecules. It is relatively good because it defines the molecule very well. We may have to rotate it a little bit, and we've got this little bit of fiddle that these aren't quite in plane because we have to bend these to make them not go on top of each other. So it's slightly distorted, but it's not that bad. The good thing about it is that it describes the molecule perfectly, and it's relatively easily it's relatively easy to mentally construct this, but it's obviously going to take us comparatively long to draw this drawing. If we get the wedge the wrong way around, it's confusing. If we need a big molecule, it's going to get ugly very quickly. So we need some other simpler ways, because the way that we had before, which was the wavy line for a straight molecule, is obviously is way more simple. This is a lot easier to draw. If we have to draw the wedges for all of the substituents, we're going to be here a long time drawing wedges and dashes, and they're just going to make my drawing really ugly. What happens when I get to here? Well, this is going to be a wedge. This is not going to be a wedge, sorry, this is going to be back in plane. It's not quite in plane really, but we've got to draw it in plane because we need to have a, this is coming up. Now we've got a problem because our hydrogen is sticking right out, or it's going right down. And we've got a problem here because this is going to be connected. So we can't connect too many chiral centers because we can't bend it all into plane. If we do that with a model, maybe it will help. So I just need to connect my model up. Let me rub that out so you've got a bit of whiteboard to see. So this is my model. If I rotate this piece so that it's in plane, a bit coming towards you, then I can rotate this piece so that it's also nearly in plane. These are actually going slightly away. So if this bit is in the orientation in plane, so I can draw it, then I can draw this chlorine, I can draw this carbon, but the problem is the next one I'm going to have to distort, and this hydrogen is actually pointing slightly towards me, so slightly in this direction, but they're almost all three pointing towards you like an umbrella. So that's a problem. If we have too many centers connected together that we need to draw, this type of diagram is not going to cut it because they get out of orientation very quickly, and we're going to have to distort the molecule very much to be able to imagine it like that. If we only have a few centers that we need to draw, and most of the molecule is simple, then we can use this system. We obviously have to imagine a little bit of a bend in the molecule. We will have to distort it a little bit to get the centers that we need to draw into the orientation that we need, but that is okay. But it does have very big limitations for biological molecules, because biological molecules tend to have these centers very close to each other, and then we have a big problem. So if we take the same molecule, we could also orient it like that. It's really difficult to get it in the right organization for you. We could also orient it like this, so that it's square. This makes it a lot easier to draw. So we can then draw it as a cross, like this, where two of the components are coming towards us and two of them are going away, and then we need a convention to say which one that is. Obviously, if we don't have a convention, then it's unclear whether it's like this or like this. So we need to have a convention that just says horizontal ones are pointing towards us or horizontal ones are pointing away from us. We would call this a Fischer projection, and the convention is that the horizontal atoms are pointing towards us. So we can draw that as these pointing towards us like this, and the vertical ones are pointing away from us. This is a type of projection that enables us also to draw one center, and it also has a problem when we get to the next center, but it has a convention that deals with that slightly better. The convention for Fischer projections for drawing centers that are next to each other, so carbons that are next to each other that we need to know the orientation of, is that the carbon chain is drawn vertically, and you imagine when you're drawing it that you feed through it, like if you've got a rosary or whatever, I guess Catholics do rosaries, that you're going through the atoms one at a time. Let me get my chain again. I keep taking it apart so it's not very obvious. So we've got our chain in its normal configuration, but if we were drawing it, we would put the first one, that's this one, into the correct position first of all. And now we need to measure the next one, which would be this purple one. So we have to rotate the molecule so that it's in position and draw that one. And then we rotate the molecule so the third one is in position, and that would be this one here. And we can draw that, it's like that. And then we can draw that molecule. So in every position, we have this shape, but we imagine between drawing each carbon, we rotate it again so that the next carbon is also in the correct configuration. That means that it's not a position that the molecule can actually ever be in, because it's actually rotated into a ring. So if we look at it like that, we've made it into a ring and we're rotating through it. But so it isn't a position we can actually look at a molecule in. It's not a position that is realistic, but it is good for drawing. And then we can draw these centers one after another in the flat-ish or in the nominally flat configuration and put our substituents on the end, and then it looks simpler. It doesn't make it simpler, but it looks simpler, and that also makes it quicker to draw, which is the whole point. The third possible type of way of drawing it would be to rotate it so that one of the bonds is completely out of plane. In this case, it's pointing away from us, and then we've got a triangular shape. So here we're trying to draw a 3D molecule, and we're putting two in plane. So we put two of our bonds in plane, which means that two of them aren't. We've got this one which says, okay, we'll put it in a position that's in between, which is geometrically simple to draw because it looks like a cross. And we'll just use a convention to say which ones are pointing out and which ones are pointing in, and it's that way instead. And then the third one is we want to look at it this way because then we've got a triangle instead, and whether they're pointing towards us or away from us will be determined by the position of the atom. Then we will typically use, or that is a typical system of drawing for a bond between two carbons, so a molecule like this, where we've got 2 carbons, and then the black carbon, this one here, and the blue, this blue atom here will be the 2 that we will be interested in, because this particular system is very bad for drawing anything more than 2 atoms, so all of the rest will be just written as a formula, and then we would look at it from the end. This would be the typical position which we had before in an so where the atoms are not over one another, but of course it can rotate. So we have to imagine it rotating or being free to rotate like this, like a propeller. This one can rotate in the other direction or in the same direction, we don't know. It doesn't make any difference. But for convention, we would like to draw it with them not eclipsed, because it's a lot easier to draw them. And so we can draw this with the ones on the end. This is the face that we're looking at, as bonds. We would draw it like that. And then the ones at the back will be hidden. So if we draw that to be the atom on the end, the front end, we can see the bonds coming towards us. That would be our atoms in the middle. And the ones on the back are hidden. We can't see the back atom, and we can't see where they're coming from. And those will be sticking out at the back like that. So it's another way of drawing it. We can rotate this to the side as well so that we can see it a little bit better, which would be like this. So that's 2 possible ways of drawing it. So this is 2 other conventions that we can use to draw our molecules. We will consider those a little bit more. One of the problems, one of the challenges that I will give you is converting one of these to another one, because they are all showing the same thing. They're all conventions to make it easier to draw molecules, and obviously they're not very useful if they don't show the same molecule. If you can't draw all molecules with them, we should know which ones we can't draw. So we've got that here. If we've got too many stereocenters next to each other, we run into a problem. This is one way of solving the problem, but it only works if they're in a chain. So if it only works if the stereocenters are all, it can be all put in a line. If they're in the side part, we end up with a problem, because how do we make it go around a corner? It's almost impossible. So this turns out to be useful for biomolecules, because they are polymers, they're chain polymers. The interesting part is all in a line, and then there are side groups. This is very good for drawing 2 stereocenters next to each other, for drawing small molecules, for deciding what's happening when they're rotating. But obviously, if there's a big part on the molecule, we can't draw that at the same time. We can focus in on these 2 atoms and what's connected to them, but we can't define something along here as well. So if we've got a big group on the bottom here, which is the same as one of these, I've actually drawn it rotated compared to the other one, but never mind. If we have a big group on here that will be something with another chiral center on it, then we would have a problem defining it here. We'd have to just give it an E, Z, or R and S, which are the equivalents for chiral centers for 4 different substituents on the same carbon. So we would have to give it a letter to describe it, because we can't draw it on this particular version. That's good and bad. It's good because we can make it easier to focus in on the thing that we're looking at. So if we're looking at the chemistry or physics or spectroscopy, something that's happening, biology maybe, that's happening at this part of the molecule, then this is a good way to focus in. If we draw the whole molecule, it's very hard to work out which bit we're talking about. But obviously the other types are better for drawing the whole molecule.